Hi.
Hi.
So please introduce yourself.
Hi, my name is James Tandon. I am CEO and founder of Cassia.ai.
Hi.
Hi, and I'm Mark Greenberg. I'm VP of Product for Cassia.ai.
So we were talking about the state of the industry is going crazy with the AI right now. What's happening?
Well, right now, people are in an arms race to get as much compute power as they can so that they can deliver the best models to the people as quickly as they can. So it's like the internet 25 to 30 years ago. We did not know what was going to happen. It was the Wild West, and many venture capitalists, many companies were trying to just dump money into the market to get as many users as they could, as fast as they could, and decided that they would just try to monetize it later. 25 years later, Google has already taken over the industry and they've been dominant for about 25 years. Facebook is very dominant as well in the social media space, and people are building their ecosystems, building their products on top of the backbone of the internet and how it is set now. And similarly, AI is moving in that direction.
Yeah,
right?
so it's a real race for users, right? People want users of their AI models, of their LLMs, whatever they're using AI for. People are out there for users today. And right now, there's a huge amount of capital going to the business of AI, and basically trying to win those users and do it at almost any expense. People are like James says, going to monetize it later, worry about getting the users now. So there's this sort of artificial condition that's been created where almost like money doesn't matter right now, but very soon it will, because the people who are funding this aren't going to fund it forever until they actually start returning some revenue on top of all these models. So something's going to happen, and there's two different approaches to this, right? One of them is you've got to save money per token that you generate with AI. The other aspect is you win more users by generating tokens faster or more accurately, or being able to do them better in some way. So there's two different ways of doing it. Both approaches need work, and that's what we're here to do.
It feels like we are in the Western. We're in the West, the Far West. It's called in the French, right? Where the gold rush was, and it's again a new gold rush here, right?
Yeah.
And it's like when we're talking gold, like they're investing so much gold right now into it, like it's hard to count. How big is this business?
This business is obscenely large, and when you look at the economics, people are dumping money beyond belief into it. But when you think about where we are going with AI, it's all based on compute and high performance computing. And so larger companies are in an arms race to purchase more compute, more higher performance computing architectures, to build data centers, and to deliver the most highly trained models based on the largest corpus of human knowledge possible, right? But in this arms race, we're also starting to come up against the power ceiling. So the power wall is coming, and we can actually see us bumping up against the ceiling today. In Singapore, it was illegal to build a new data center until very recently. And the only way you can build a data center now is with a whole bunch of applications and a whole lot of scrutiny for something as small as 5 megawatts. Now compare this to the 5,000 megawatts, 5 gigawatt data centers that Sam Altman of OpenAI has indicated that he wants to build. And you need to do some math and think, well, if you build 5 gigawatt data centers, as suggested for just OpenAI, then you're going to increase the power consumption of humanity by 1%. Now, think what happens if you have multiple companies in competition and it becomes infeasible. There is going to be a problem, something has to give. And it's not only in Singapore. We also see around the Washington, D.C. area, near the Washington, D.C. and Virginia. There are limits placed on new data centers there. The lead time for a new data center in, San Francisco Bay Area, Silicon Valley, it's 5 years. So there's no way that we can build out too many more data centers. We're actually bumping up against the maximum amount of peak power in this case. We can build it out slowly, but we need new methods approximate computation is something that we propose.
It is my understanding that there's one company making a lot of money and everybody else is just I'm just joking a little bit, but there's NVIDIA, like everybody wants to buy this stuff. And then there's other startups doing different kind of ASIC or accelerators or something like that, right? Kind of. And of course, there's a big Intel ARM ecosystem and everything. But is it possible that they have a vested interest in not seeing a complete alternative?
Oh, you mean NVIDIA
Maybe
seeing a complete
something
alternative?
that might be revolutionary, which maybe you're talking about.
Yes. So keeping the status quo is very good for NVIDIA because they're making a whole lot of money and many people want to use their chips because it's based on not only their chips, the current ecosystem is based on not only on their chips but also on a software layer called CUDA, which is then built as a lower level to, say, PyTorch and TensorFlow. There's a lot of work to really build that out, and so there's a very large moat there.
Yeah, if you're winning everything, then why would you change anything, right? And that's an important aspect, right? But that also creates an opportunity that if somebody's going down a particular path, there's an opportunity for people to come along the paths that have not yet been traveled, and that's kind of the direction that we're going here.
So now I think there is a whole thing in optimized computing, and maybe the instruction set is much more lean on the ARM ecosystem maybe, and all these mobile phones are like billions and billions of people are buying them, and it's more optimal. Are you talking about being more optimal in terms of power consumption and hardware design?
Well, if we look at some of the recent AI chip architectures, right? What's happened over like the series of different architectures of the leading AI providers, their computing capability measured in flops has grown like 100x in 2 generations, I think it is, something like that. And you have to ask, okay, well, how did they get this growth, right? They didn't get the growth from optimizing an instruction set. They didn't get the growth by tweaking a CPU. Where that growth came from was a massive increase in the amount of matrix multiplication that these chips can do. And what we've seen in all the major AI chip architectures over the last several generations, they're all doubling the amount of mathematics that they can do, the matrix multiplication that they can do, roughly doubling every generation. And that has been what's driving the increase in computing power. And then that's what enables these giant large language models to be able to run on the computing hardware, just because we're spending capable of doing so much math in these chips. But at the same time, they're growing in power, right? We were there at the conference there today. There's people with cooling systems that are 100 kilowatts for a single rack. I can't even imagine what a 100 kilowatt heater looks like. A 100 kilowatt server in one rack, and then they have to cool that thing is incredible. There's incredible amounts of power going into this stuff. And that's kind of what we're here to address.
Yeah, and when you look at just the single chip, if you look at the data sheet for one of these highest power chips, it says on the data sheet only 700 watts. But when you think about it, right, you still need to cool that. You're going to put that into a system with hundreds of other chips, right? You're going to put that in there and you're going to have a problem with cooling that. And so that's going to take energy as well. And so the net energy cost or the net power cost is going to be north of a kilowatt for several of these chips as a result.
And you have multiples of them per rack, right? You have a rack mount server. Typically there might be 4 or 8 of those chips. And that's not the only thing that's consuming power in the rack. We have memory devices consuming power. We have the other communications, the rack level communications. All that stuff consumes power. So we have a giant rack full of servers, and very quickly you can get up to tens or even over 100 kilowatts in a single rack just from doing AI computation, because there's a massive amount of computation that gets done.
So these cowboys are in the gold rush, right? Trying to get to the next big thing, investing so much money, but maybe there's a way to do things differently. Maybe there's a way that things can be more optimal, and there's some talk right now, some What's happened in the last few days in this area?
Well, in the last few days, we've had some excitement with people rediscovering approximate computations and some new ways that are not necessarily quite so new, but some variations that actually make multiplication go incredibly fast for AI. And so maybe 60 years ago, Mitchell brought in a special approximation which made multiplication go extremely fast. Now, unfortunately, when taking his approximation and applying it directly to a neural network, it causes the accuracy of the network to drop precipitously. And several other researchers have actually looked at this and made a comment that this is not the best way to do it, because if you see a 6% drop in your accuracy on a ResNet model, calculate where you're trying to classify whether the image is an airplane or a dog or a cat, right? Then that's not really effective. If you can have maybe 1 to 2% accuracy, that's a little bit better, right? Depending on the application, this may or may not be acceptable, but unfortunately, Mitchell multiplication used directly was not able to handle that. But with some modifications that we were able to discover some years ago, we were able to enable the ability to use logarithmic-based multiplication to improve power and performance for AI models with it.
So you have a presentation here about your company?
So in this presentation, it was last year in 2023, September. I presented it at the ICICDT conference. And so this conference, we presented the matrix multiplication algorithm and how it was implemented using some augmentations, introduced some of the methods that were used for approximate computation in the past, and what we proposed, and some of the results that we have found with neural networks using it.
Is all this stuff with the AI and LLMs and everything very, very high level mathematics, or how does it work?
In my opinion, well, there are a lot of people who spend time thinking about how to put the models together in the best way possible, and people spend several years getting a PhD to build these models and come up with new techniques to do it. But when you look at the model mathematics and you go and look at the details, you'll see it's based on matrix multiplication and something called activation functions. So an activation function, right, is going to be a few nonlinear functions. So a very simple one is to say, if the input number is less than 0, then output a 0. If the input number is greater than or equal to 0, output that number. This is called the ReLU number, or the ReLU activation function. And there are several activation functions that that are variations on this, that turn ReLU into a fully continuous function and are better behaved. And so these kinds of functions are used in the LLMs in addition to the matrix multiplication. But taking some time, I think anybody can pick it up.
And so what would you show here in your presentation?
Now here I can show you some of the details. It's a presentation that's geared towards people who are chip designers and more at the PhD level, but I can explain it, some of the details for more of the layperson if you like. So in this presentation, I was comparing it against quantization. And so are you familiar what quantization is by any chance? And
please explain.
Yeah. So quantization, generally we use a number. When we represent a number in a computer, it's maybe 32 bits or 16 or 8 bits. Now what you can say is, instead of storing a number as 32 bits, you can store it as 8 bits or even 4 bits. And you can represent that same number using a smaller number of bits. The problem with going to a smaller number of bits is it makes your number representation more inaccurate. So you have to round up or down to finally get the number that you want. And so what we are proposing here is to do something besides quantization. quantization is used to improve performance and reduce power. But unfortunately, this does not allow for training in several circumstances, and it's also a loss in accuracy depending on the situation.
It sounds like it could be compression. Does it have to do with that?
Well, compression typically will preserve data, right? One of the issues that we have with quantization is that quantization literally just throws some data away. And we don't know, is it good data, is it bad data? We just, if we quantize from 16 bits to 8 bits, we're throwing away 8 bits. What was in those 8 bits? We don't know, we just threw them away, right? There's no, it's a very brute force approach of reducing the amount of data in the neural network, right? So we have some more elegant ways of doing that, which we can actually do and do them in, even more efficiently than quantizing, right? So I'll throw a data point out there if that's okay. Our floating point 16 multipliers are smaller than the traditional way of doing a floating point 8 multiplier, right? So you actually keep the full 16 bits of accuracy without throwing the data away, and improving the silicon area, and the power and performance gets better too.
All right, so let's have a look at your presentation.
Yeah. So really, this is just an outline of the presentation here. I'll give you a little overview, talk about some previous work, and then go into what we call the floating point logarithmic number system that we use to represent our numbers. So approximation of arithmetic. What we can do with approximate arithmetic is come up with a way to perform that computation with fewer logic gates or fewer transistors. So when you think about how we build computers, we use transistors, which are nothing more than an on-off switch. So you could think of like your light switch, right? And when we want to implement, say, a multiplier, then what we would do is we would implement it as a series of adders. So what is addition? You have a number and a number with multiple digits each. Say you have 10 digits and 10 digits. Then you add up column by column. It's the same with binary, only with binary you're using ones and zeros here. So you could think of each of these as taking two numbers in and then adding two numbers at a time. With multiplication, you have to add 10 10-digit numbers. In this case, it's using, I believe, 8-bit numbers. So 1, 2, 3, 4. So 7 adders for 8 numbers that need to be added, right? If we quantize, i.e. we use 4 bits to represent the same number instead of 8 bits, then we would use 4 stages instead, right? So it's a much smaller implementation, so you use fewer transistors. So in this box here, this would represent a 1-bit computation. Right.
How do you make sure that all the data or all the functionality is on the smaller version too?
You don't, right? In this case, you don't know that the functionality is there. This is the problem with quantization, because what we do is we can take only the top bits, and we only look at the top bits here, and we keep that, and it's rounded off. And so the least significant bits are thrown away, and you can also have a scaling factor so that it can scale up or down based on a 32-bit number. If you have a large matrix or tensor of numbers, as we say, so that would be a multi-dimensional array, right? Then you would be able to scale that tensor or some row of that tensor according to that scaling factor. And then you can have numbers of any size represented by the scaling factor and the quantized number. Right.
So you are suggesting to do this differently?
Oh yes. So other than this, there are partial product approximations, as well as the partial product tree, approximation compressors, and Mitchell's method, which I mentioned earlier. And I want to focus on this method here, the log of 1 plus x. So this is log base 2, right? And if we're taking the log of 1 plus x, as we see here, we can approximate that to the value x. So maybe an impromptu look I can show you right here. We could actually go, would you like to go to a graphing calculator? We could do that. What are your thoughts? So we could go to maybe load up Desmos here.
While he's doing that, maybe I'll point out, we're not against quantization. In fact, our technology is compatible with quantization. But what we're saying is that you don't have to quantize, that there's another way of doing this that actually preserves almost all of the data without quantizing. And then that also increases the possibility of doing other approximation techniques, which also exist within neural networks. Another technique that you may have heard of is called sparsity or pruning. That's another way of removing redundant data from the neural network. Especially in inference. And the key thing is, with sparsity, especially if you have use some of the more advanced techniques for sparsity, you can choose what data is relevant and what data is not. So in a neural network, James talked about the activation functions earlier. Neurons that are consistently producing numbers close to 0, we can actually remove them from the neural network. And that's a technique that technique of sparsity works extremely well with the Cassia.ai technology, but is allows to keep the resolution of numbers available in the case of that you keep the relevant neurons that are actually producing useful data and just removing the neurons that don't do anything.
Does it take a lot of performance to do that sorting, to make sure that you don't use the ones that are useless?
So we do. I mean, that's part of the training algorithm, which is a hugely computationally intensive process. So, but as part of the training mechanism, we'll find that, for example, in a fully connected neural network, that there's some nodes that just don't do very much, right? So you might as well just remove those from the neural network. That technique doesn't work as well, especially if you start quantizing very heavily. So there's a kind of competition between, well, okay, do we want to quantize and just randomly throw away data? Do we want to introduce pruning and sparsity where we're choosing the less relevant data to throw away? And we like that approach very much. And the Cassia.ai technique is especially compatible with pruning and sparsity. So that's something that again will help to propel this forwards.
Mm-hmm. Yes, and so coming back here, I just want to highlight that what we are going to do is we're going to look at some of the math functions now, right? So if we look at here, log of base 2 of 1 plus x, we're going to get a graph like here in the red. And what we want to do is we want to zoom in, and I want to highlight this point that this intersects at point 0, 0, and it intersects at point 1, 1. So we have a nice little curve right here, and this is the log of 1 plus x. And this function is going to be important now because we're going to compare this with the function x. And we see that here, if we have a 0 point here and a 1 point here, they're going to be equal. And this curve, the total difference from here to here, right? The difference between these two is very, very small. So when we go to solve our problem with multiplication, right? We multiply numbers in the standard domain, but if we take the logarithm of two numbers and add the logarithm of those two together, then that is the same as multiplying, right? So what does that mean? You could say a times b is equal to the log of a, or the log of a times b is equal to the log of a plus the log of b. So if you have a fast way to go between the logarithm and the standard domain, then you are able to reduce multiplication to addition. And the key path to do that is by using this approximation. So the problem, though, is that there is an error bound right here. And so that error bound is there's an error right here, and that error is fairly large. And this causes a significant drop in accuracy in the neural network. But what if we say, instead, we use a value plus c here instead, right? And then we use C is equal to 1. Let's say set that equal to 0. This is the standard case. But let's say we set this to 0.03125. And you see that the error reduced. It got smaller. And this blue line is now closer to the red line on top. And then there's more error here at the bottom, at where the input is 0 and the input is 1. So it's a little bit above and a little bit above here and here. But the nice thing is the worst case error is reduced. And this causes us to have better accuracy in the multiply, the approximate multiply, and gives us better accuracy in the neural network.
So this is a key point, I think, of understanding here, is that this is approximate math, right? You can do math the way that, everybody, you learned how to do math in grade school, where you line up the numbers and you multiply and you add, right? And that's a very slow process, and it's a very slow process also in binary. By using this technique, it's a much faster, much less computationally intensive way of doing the mathematics, but a small error is introduced, right? Now, does the error matter, right? And I don't know if you want to get to this in a moment, but I'll give you a preview. The error doesn't matter. And we'll get to that in a moment, and to why that error doesn't matter.
Yeah, so this is error at the multiply level. And we need to remember that when we use a neural network, we're talking about millions, if not billions, if not trillions of multiplies. And if we're talking about large language models, we're talking about 405 billion weights in some of the largest models to, I believe the largest model I have ever heard of has maybe 13 trillion weights. Now that is absurdly large when you think about it. That's a lot. That's a whole lot. Most modern computers, when you purchase off the shelf, your regular motherboard usually is limited to about 256 gigabytes or 0.256 terabytes. We're talking about 13 terabytes of data minimum, if not more.
In these very large models.
Yeah.
And they're not done, right? Mm-hmm. Like we said, there's a race for even more and more users. Another way of getting users is to make those models smarter, which means training them on more data, which means actually making them even larger, right? We're not even done yet on how much data we have to train. We have, at some point, all of the data that's ever been created by humans to train upon. We're not even close to that yet, but we will be in a few years, and those are going to require incredibly large models to store all of that data. So we're still moving in a direction where it may be necessary to have even larger models than what we have today. But by the law, some of the laws of large numbers, and you can probably talk about this, with these very small errors that occur in the individual multiplications have very little effect when we consider the output of the entire neural network.
So some of these companies like Facebook, Google, Apple, they're making smaller versions of some of these models that run on phones.
Yes.
What is different between what they're doing and what you're suggesting?
So a lot of what they're doing right now to make these models smaller is they're using very, very aggressive quantization along with optimization of the models to focus it towards applications that would be useful at the edge. So you don't need a large language model that is fully general, probably in your cell phone to run locally. And it just wouldn't run in your cell phone. If you needed to run it, you would need to run it on a server to be able to get much better performance. But if you focus that and you optimize it, and you're willing to take a lower level of accuracy from the model, then and it's useful for the user, then it's okay to make it smaller using these techniques. And so where the key difference comes with our technology is that it's a new technology that is parallel to quantization, because you can reduce the number of bits from 32 to 8, from 32, which is used, or 16 used in training, and then reduce it to 8 bits or even 4 bits. And if you're staying with floating point numbers with a floating point lumber system, you have a biased logarithmic number system imposed upon the floating point number format. So when you're converting between what would be a logarithmic number and a standard number, a standard floating point number, it's a very quick calculation. It's a very simple addition to solve that problem. And so implementing that as a circuit, that's the same as having maybe 2 to 3 additions instead of a full multiplication. So if you have an 8-bit multiplication, it would have 8 numbers cascaded for the 7 adders there. So if you're looking at the circuit, right, if you have a floating point number, it's already in a semi-logarithmic format. What we're doing is we are approximating what's called the mantissa. And so I can go over that on my whiteboard in a little bit as well. But really what it comes down to is treating what is a floating point number as a fixed point number, or just as an integer with a decimal point. And then it's a sign magnitude. So you have 1 bit which says 1 for negative, 0 for positive, and then your standard binary number for representing an integer with a radix point. This is like a decimal point, but for base 2. Right? And if you treat this as a biased number, i.e. you have to subtract a value, and then it will be equal to that real value as a logarithm instead. And then you can perform operations on that number in the logarithmic domain, the fixed point version of it, and then once you've finished your computations with, say, 2 numbers in the logarithmic domain, you can then treat the result as a floating point number, and it's already computed. You don't have to do more than a little bit of computation with the bias.
How much lower power consumption are you suggesting you could run full AI?
So how much lower power consumption? It really depends on which level that you think and how that you're thinking to examine. At the operator level, for a single multiplier in a 16 nanometer technology that we looked at, if you apply this technology, you can reduce the power consumption of that multiplier by 23 times for a 32-bit multiply and 10 times for a 16-bit multiply in floating point.
So when people are talking about cutting edge chips made in Taiwan on 3 nanometer, second, third generation, stuff like that, could you be involved in optimizing what comes out of those?
Absolutely. This technology is independent of a technology node. So if the next technology node comes out next year, we are going to have the ability to go right to it, because it is a chip algorithm. It is a chip level algorithm, and there are special tools that can take a specification in a language that is called Verilog. And you take these special tools and you can convert it to this technology, whether it be 16 nanometer, 3 nanometer, 2 nanometer, 18A, or 12A, depending on which technology that comes out. I believe that there are several on the roadmap right now.
And so is your company involved working with chip designers to make new chip designs? Or yes. Where's the technology fit?
Right now we are working with other chip designers, because there are more than 100 companies right now who are working to build chips. Like you said, it's a gold rush, and there are cowboys in the Wild West who are working their butt off to try and be the ones who get the most users for the next big thing, and many, many competitors in that market. And to build a chip, it takes millions of dollars to bring it to market. Rather than try to spread ourselves really thin and do what everybody else is doing. And really, it makes no sense to try and keep this within a single chip ecosystem. What we would like to do is to partner with any chip company that would like to bring Approximate technology to their users. And so we are working with several companies right now to bring this technology to them.
What is the best architecture for the chip?
The best architecture for the chip, this could be controversial. In my opinion, it depends on the application very much. So Google found very good results with their TPU, and they used a systolic array in their TPU v1, and so they got incredible improvements in the power consumption and were able to get much better results compared to the NVIDIA GPUs. That being said, when you look at the GPU architecture that NVIDIA has produced, it's much better at handling, say, more generalized operations, I would think, because it's designed for a different problem domain. Originally, it was designed for doing graphics processing, and so that architecture has evolved from there. AMD has a very strong background in general architectures as well as NVIDIA, and so they're trying to, and Intel as well, they want to cover all the major problem domains. But if you're looking for a focus domain, you could look at a company, say, like, you could look at any number of companies, like Grok has their own custom TPU, SambaNova has their own custom processor. Then you also have SEMA has another one as well. There are many companies that are working on these processors right now. And it really depends on the application as well, because there's also not only the cloud, but you also have the TinyML chips. So I believe there are several companies that are building, say, ARM processor cores with accelerators on them.
But there's one thing that all these architectures have in common, and it's multiplication, right? They all do extensive amounts of multiplication. And like I said earlier, all the architectures from the largest AI companies have been doubling the size of the multiplication units that they have with every generation, right? So the multiplication is growing at an exponential rate. The other functions, what we call GPU floating point operations per second, that's increasing roughly on a linear rate for most people's architectures. But almost every architecture is doubling the size of their TPU operations, their tensor operations, which are these matrix multiply operations. Those operations are doubling with every generation of chip. So this is exactly where we want to be. Everybody is doing this. They're increasing the amount of multiplications, and until something breaks. And we're offering a technology here where every time you do a floating point 16 multiply, you're going to use 1/10 of the power. We're giving people a lot of opportunity to be able to continue to increase the size of their tensor processing units and their matrix math functions.
So on the calculator, there's the X, right? The multiply. Are you offering like an alternative?
Sort of. Right? Now here's the thing. Would you use this for an actual calculator? Maybe not, right? Do I want to use approximation for my Excel spreadsheet?
It depends on the application.
Maybe.
It depends very much on the application. So a lot of people have asked questions about other applications, and we're exploring those right now. What we've focused on, though, is right now artificial intelligence and machine learning, because this is really where a lot of people are doing the work right now. It's where a lot of the jobs are being made, or shall we say startups are developing their jobs and doing a lot of R&D to really see if they can be first to market to bring a good product to market, and it's a gold rush.
Can we talk about our results where we, the accuracy of the neural networks when we introduce this approximation?
Yeah, absolutely. So we already see this comparison here. So if we look at what the multiplication looks like here, so accuracy. ResNet 18, this is a convolutional neural network that was used to measure or to do classification of images on the ImageNet data set. Now, if you look at the standard accuracy, when you pull it from the PyTorch library, it's 69.76% accurate. So almost 70% of the time, so 69.76% of the time, it's going to get it right. The rest of the time, it will guess what the object is wrong. This right here in 9, this is what happens if we use just a straight Mitchell approximation to do that inference. So if we take a model that's already been developed and we don't want to take the time to retrain it, we just want to work with it, and we try to use the Mitchell approximation directly, it's going to cause, as you see here, a drop of about 4.5% in the accuracy. If you go to a larger network, it can go as high as 6%, right? And when you use our approximation where you add that extra constant and you get that approximation really close and you reduce that worst case error, then you are within 1%. So it's only 0.5%. No, actually it's 0.5% right here is the drop in accuracy, right? So this is within error bounds for a lot of applications, because 2 or 3% on a human for a human application when you're working in person tends to be admissible. So this is very, very useful for a lot of applications.
Right.
And yeah.
A 10x reduction in power in the multiplication for less than 1% error in the output of the neural network.
Yeah, that's if you're going to be doing 16-bit, right? And when you look at that, it doesn't just work for ResNet 18, but this works for several other models as well, and we're showing accuracy losses less than 10% for all of these across MNIST and ImageNet. And we have new results right now. This is an older presentation, but we have results showing, we have results from, say, CFAR as well, MobileNet V1, V2. Also, we've looked at transformers more recently. GPT-2 had very little loss. It's 0.04 on the HellaSwag dataset. We have also, we were able to use it to train the DLRM recommendation model from Facebook Meta. That model was trained within 0.053% accuracy. So we were able to get very close. It's almost the same as a result. And when you look at what the size looks like, so these stars represent standard floating point formats used in the AI ML ecosystem right now. And when you think about how big a multiplier is actually going to be on a chip, so think about like a systolic array, right? You're going to have a whole bunch of multipliers and adders put into a 256 by 256 matrix. So you have more than 65,000 multipliers and adders in a big matrix. And so if you look at this, a 32-bit multiplier, if you put that in there, it's going to be extremely large. And so you want to reduce the number of bits as much as possible, and you can reduce the size of the gates by a significant amount by going from 32-bit to 16-bit, right? But what is wonderful about approximation technology is that you can take that 32-bit multiplier and then use this approximation technique, and you can bring it down to a value that is less than 500 logic gates. Now notice, if you look closely at this graph, it is smaller than the size of the 16-bit multiplier. Your 32-bit multiplier is smaller than the size of the 16-bit multiplier. The approximated with Cassia is smaller than standard. So if you have that extra capability for accuracy, why not use it? Why not use it? And the nice thing about this algorithm here, this is an approximation, right? And so you can actually perform the computation, and you can you can actually find a value that's very close, if not the same. And it gives you better accuracy as a result. So you can invert that operation if you wanted to as well. On a chip, you can see standard multiplier to a smaller multiplier right here. Any questions? It's a difference in size of a factor of 10 for a 45 nanometer process. And when you look at this one, you can see the reduction in the number of standard cells. These are logic gates. And so These are estimated area, latency, and power consumption for the multiplier right here. Yeah, and so, other questions, please.
You're talking about 10 times more efficient. Is there any chance you could do it like 100 or 1,000 times more efficient?
Cascading with other approximation techniques will bring this to you. So Mark mentioned some of the other techniques that are available. Besides quantization, that's one form of approximate computation. This is another form of approximate computation that we're presenting here. Then there's also, say, sparsity, where you can reduce the number of neurons, right, effectively. So some of those neurons in a neural network are very important and you need to keep them there. Others are unimportant and the value of that neuron goes very close to zero in the middle of training and you can ignore it. If you add that capability with this this approximation technology, with sparsity, with quantization, where you reduce the number of bits, there is a cocktail that can definitely get you much better performance and much better power on the orders that you suggest. Yeah.
Are you talking about running whatever runs on a hundreds of watts NVIDIA chip down to a smartphone?
Down to a smartphone. So using techniques to approximate the network with sparsity, quantization, and by using our techniques here for approximation of the multiplication, we believe that significant improvements in the performance and the power can be realized. And even though many techniques are already in use, this one improves it by another factor on top of that.
So with this technology, potentially we could be running the most advanced AI offline on a little ARM-powered device.
Potentially. It depends on the application, it depends on the model, it depends on how well it's optimized and what the drop-in accuracy is, and also depends on the use case. So some use cases will only tolerate 1% loss in accuracy, another use case may tolerate, say, 10% loss in accuracy. I've spoken to managers in the robotics domain who have said that some inaccuracy of a higher percentage is really not a big deal for some of their applications. And so they're very happy to work with that in some cases. You don't need to have perfection all the time, which is a very good thing.
And that's a unique property of neural networks, right? Again, for standard computation for an Excel spreadsheet, we both went maybe, right?
Yeah.
But for a neural network, they're resilient to error. That's one of the things. The neural networks that we use today, in many cases, they are actually carrying more data in them than what they need to actually solve the problem, right? So the way to look at this is, how much data can you remove from the neural network and it still performs the intended function, right? So again, quantization is a method, sparsity is a method, and the approximate computation is also a method. But we like this method very much because of how much simplicity it brings to the computations in the neural network. Basically, as James said before, the multiplications turn into additions, and that is so much more efficient than having to do the multiplication the long way around.
So if this works, does that mean maybe some people might be greedy and want to do 10 times more on the same power budget?
Sure.
Quite possibly. Quite possibly. Some people we've spoken to were very interested in that. But other people we've spoken to are very interested in getting the smallest chip they can build possible, because not everybody wants to have a 10 kilowatt data center in their pocket, right? Or a 10 kilowatt supercomputer in their pocket. That's not possible. The battery will probably be used up in only minutes, and it wouldn't be very good. So we have to have models. If we're going to have these models at the edge, and sometimes we're going to have cases where we don't have internet access, right? So in these applications, definitely we need to have some way of delivering model capability for this AI ML model capability in a low resource setting.
And there's future technologies that we haven't even thought of yet, right? Of where AI can be applied into our everyday lives, right? Mm-hmm. We keep seeing these new applications. You've probably seen people who've got glasses with AI inside them. I saw an application for those glasses recently that will recognize people and tell you who they are inside the glasses, right? I've seen pendants that you can wear that will transcribe every conversation around you. There are these edge products that are required to be very low power because they're going to be running on a battery, and those need to run somehow. And so again, this creates an opportunity for those types of devices as well. So it works great for servers. We'll bring down the power of these great big servers that are chomping a huge amount of power, but the technique can also be used for these edge applications of things that we've thought of and things that we haven't even thought about yet.
Maybe my camera could help me frame better and tell me that I'm too close or need to get back or something else.
Mm-hmm. Sure. We were joking around just as we were setting up this call, right? This meeting, right? Getting the lights arranged in the room. It would be lovely to have an AI model that would just adjust the lighting regardless of how terrible the lighting was in the video. We're not there yet, but one day we could have that built into your camera.
And how about the old guy I'm joking with, Altman, right? He was talking about how much power does he want to use?
Oh gosh, how much power does he want to use? He wanted 5 gigawatt data centers. He wants to build 5 gigawatt data centers, I believe.
Just for OpenAI?
Just for OpenAI to be able to do training and inference for their models, I believe. So 5 gigawatt data centers, 5 to 7 of those, I think is what the number was bandied about in the news. If we do the math on that, that's about 1% of the total power consumption of humanity when we think about it. So that's really difficult to really put into practice. And we're already reaching peak power in some locations. So if you go to Singapore, it's going to be impossible to build a new data center, right? Because you have a maximum of like a 5 gigawatt data center there, right? Outside of Virginia, right? Around Washington, D.C., just in Virginia, right around there, there's a moratorium on, or there's a limitation on building new data centers there. And there's a 5-year lead time to build something here in the data center, build data centers here, right? So how do we reduce the amount of power, right, if we can possibly do that? So there will be people who are greedy and say, well, we want as much compute as we can get. And in the arms race, this is what we're going to have. We're going to have multiple companies going for that because that's how they're going to get the customers. Otherwise, they can't. It's going to have to be rationed somehow. But the market, because there's not enough power available, it's now becoming becoming a scarce resource in the optimal locations. So now it's going to become a question, well, how much compute can we get into these power envelopes when we're talking about the data center? And I believe that this technology can give a significant increase in the computation capability for these kinds of use cases.
And big tech is investing, I guess, in the uranium and solar power and wind power because they're desperate to get enough power.
Yeah, I believe Facebook Meta invested in a wind farm out in the Midwest recently, a 129 megawatt, if I'm not mistaken, power plant. They invested there so they could build a data center next to it. And so they needed the power. So there you go, power and a data center. And now if you want to build it, if you want a data center, you now need to build a power station to go with it.
And some of them are talking about thermals in the Iceland or somewhere, and they want to use the water to cool down, and it's going to heat up the water for the sea. They do too much of that, maybe.
Potentially. I mean, that is a, heat pollution of water is a potential issue. But yeah, you're correct. You're exactly correct. Every time you generate a watt of heat, as you do this computation, whatever computation you do in a data center, every time you generate a result, you're going to generate some heat. If you're generating a lot of results, you're going to generate a lot of heat. You then have to remove that heat from the data center, otherwise the whole thing melts down into a puddle. So you have to remove the heat, which is why, like you were saying, you use cold water for that. Maybe you place your, if you can, you place your data centers in some Arctic region where it's very cold. But then they're far away from the users who want to use those, and there's latency towards reaching those and stuff like that.
And you'll melt the polar ice caps.
Oh, well, maybe one day, right? So, I mean, I guess that might be happening also. And data centers have some contribution towards whatever aspect of energy that we're using in the world, right? But again, this is the point. We want to be able to help to reduce that amount of power and do it by doing computation in an efficient way.
So if this works, do you think a government are going to mandate your technology?
Mandate it? That's a matter of question. So this is an approximation technology. So it does have merits and drawbacks, because, as you saw, there was a small drop in accuracy of 0.5%. Now this is also nice. It's also nice because you can do training to recover that, and you get a recovery back to the original accuracy. But is every chip going to be using it? There are already more than 1 million chips that use exact math and use neural networks that run on exact math. And so are we going to take all of the models that we've built and throw those away? Some of those models will still need to be there. We'll still need to have both kinds of computation. And it's going to be very hard to convince a large number of people to use it if there is a use case that requires one or the other, right? But for some use cases, if there is a significant drop in power as a result, I will defer to the government institutions about that.
But I mean, power is a proxy for cost, right? We pay for energy. We pay for energy when we do the computation, then we pay for energy again when we have to remove the heat from the data center. So you actually pay for power twice when you use it. But this is the thing here. Ultimately, I think market forces will be a bigger decider rather than governmental forces, right? When we are using an AI for some application, right, the AI generates some number of tokens for each answer, and those tokens use a certain amount of power, and power is a proxy for cost, right? So the end user, who has no knowledge of any hardware that's happening in the data center, the end user, what they're going to see is, okay, how many tokens were generated? Basically, how many questions did I ask it, and how many answers did I get, and how much did it cost me to do that? Right? That's going to be what the end users are going to care about. And again, we're going to improve that metric. The next level, removed from the end users are the cloud service providers, the people who are providing these data centers. They very much care about how much power they use, because they know exactly that's their profit margin, right? They use less power, they're going to make more profit from a given amount of computation and a given amount of dollars to do that. So they're going to be very motivated to adopt efficient computation technologies, because that's going to directly impact their bottom line. And I think that's going to really be the determinator of, do technologies get adopted, rather more than, I think, government, government and, interaction. I can't imagine the law that says, I can't even comprehend how you would write a law that said you had to do computation in a particular way. But the market will tell us.
So where can people get more information?
Oh, you can go to our website immediately to get in touch with us, www.cassia.ai, and you can get in touch with us there. We also have published our paper at ICICDT in 2023, so you can check us out. We are listed in IEEE Explore, and I will be sure to give you the link to the paper so you can look it up online.
Are there many experts in this field who have many questions, and maybe some people are trying to say it doesn't work, or they?
Well, there are a lot of people asking questions about it right now. We made the round at the AI Hardware Summit and spoke to several people there, and as we spoke to more and more people, a lot of people just started looking up into the right and saying, aha, right? That aha moment just clicked for many, many people. And we were able to close several follow-on conversations from there, and things are getting pretty exciting, I must say.
All right. So thanks a lot for this discussion.
Thank you.
Super. Thank you.
Really do appreciate it. Thank you very much for your time.